In this segment of lecture, I like to introduce an important characteristic of many important chemical and physical process. It is the reversibility. The reversibility is associated with a process that can take place, then be reversed to return the system to its original state and leave the surroundings unchanged. The later part, leaving the surroundings unchanged, is the most crucial part. Taking the gas expansion as an example, if a high-pressure gas is stored in a piston cylinder device, if the pin fixed the piston is suddenly removed, then the gas expands and the piston hit the stop. In order to reverse the process, we will have to apply certain amount of work, push the piston back to the original position, and then fix by the pin. But comparing the initial process and the reversed process, the reverse process will have to do more work because the gas is at a high pressure. We will have to apply relatively high pressure than the original process. The original process, the piston faces relatively low pressure, so relatively low work is involved. So comparing the initial and the reversed process, we conclude the environment, the surrounding has been changed. Therefore, the process cannot be considered reversible. Alternatively, if we modify the process by applying a group of weights on the top of the cylinder, and that those weights can be removed piecewisely to induce gradual change of the gas volume. And the process can be reversed by putting additional weight back on the top of the cylinder. This is near reversible process. We encounter many irreversible processes in our lives. This slide shows 3 examples. If we use our car brake to stop a car, essentially the brake converts the kinetic energy of a car to the internal energy of the brake, because the temperature of the brake rises. Eventually, this temperature dissipates, but we cannot use that energy for moving the car. That means we cannot convert the energy dissipate to the environment to the kinetic energy of the car. Therefore, it's an irreversible process. The second example on this slide involves stretching an inelastic spring until it deforms. If we use the thermodynamic terms, we provide the work to the spring. we convert the work to internal energy of the spring, and that internal energy becomes the deformation energy. This energy cannot be used to restore the shape of the spring, so the process is considered irreversible. The next example involves using electrical energy from a battery to heat up a resistor, and the heat from the resistor eventually released to the environment. That heat cannot be converted to electrical energy directly without additional work. So the process, the electrical energy applied to resistor cannot be considered a reversible process. This slide contains 3 additional examples. At the top, we have a container. Gas is at one side. Vacuum is at the other side. They are separated by a partition. If we remove the partitioner, the gas rush to the vacuum side. This process cannot be considered reversible because we have to do some work to push the gas to the original volume. And so we change the environment, and the process cannot be considered reversible. The second example on this slide involves contact of 2 objects at 2 different temperatures. So the heat from the high temperature object is transferred to the low temperature object. If the temperature difference is significant, according to the second law of thermodynamics, we cannot move the heat from low temperature to high temperature without doing additional work. Therefore, this process is also considered irreversible process. Now, however, if the temperature difference is very, very small, if we consider the difference a differential form, dt, then we can consider the process near reversible. And the near reversible will be considered as a model process for heat engine in the subsequent discussions. And the last example on this slide involving 2 gases separated by a partitioner in a container. If we remove the partitioner, the gas mix. And this mixing process cannot be considered reversible because separating 2 different gases requires additional work. So our next topic is closely related to the discussion of reversibility. Our topic focuses on a specialized heat engine. It's called Carnot cycle. The Carnot cycle has highest possible efficiency of a heat engine because it has the following characteristics. Number 1, it has the 4 unit operation as a common heat engine: boiler, turbine, condenser, and a pump. But all of them are operated under reversible conditions. When the reversibility is applied to heat transfer in these 2 unit operations, we can say that the temperature difference between the reservoir and the working fluid are very, very small. And furthermore, we assume the pump and the turbines are operated under adiabatic conditions. That means though there's no Q terms involved in these 2 unit operations. As a summary, these 4 processes for a Carnot cycle involve 2 isosomal processes and the 2 adiabatic process. 2 isosomal, 2 adiabatic. And all of them are reversible. If the working fluid of a Carnot cycle is an ideal gas, then on the PV diagram, we can tell the state of the 4 conditions of the fluid can be represented at 4 points. They are linked by 2 isosomal processes and the 2 adiabatic process. And that involve absorbing the heat isosomally, adiabatically along this isosomal process. Then the turbine does work adiabatically. Then the heat is rejected to the low temperature reservoir. The working fluid is pumped back to the original state. On this slide, we are going to demonstrate two propositions. Number 1, we claim the Carnot cycle has highest possible efficiency, so that no irreversible process can have the same or even larger efficiency than a reversible Carnot cycle. The way we prove is to prove that it is impossible to have a irreversible heat engine having higher thermal efficiency than the Carnot cycle. If it does, then we can combine a irreversible heat engine with a reversible engine. In this combination, reversible engine absorb heat from a low temperature reservoir and reject the heat to a high temperature reservoir, and a certain amount of work it has to be done. And if it is combined with a irreversible heat engine, then that means we can absorb same amount of heat as the refrigerator reject the heat, same amount of heat. Absorb this same amount of heat from high temperature reservoir to this irreversible heat engine. And this heat engine provides higher efficiency. If we can provide higher efficiency, that means we can withdraw only part of the work back to the reversible engine and complete the cyclic process. And then more than that, we can withdraw certain amount of work done by the irreversible heat engine as useful work. Then if we take the control volume like the dashed box, we realize the net result of this combined process is work done without doing anything else, which violates the second law of thermodynamics. And so we have proved the proposition 1. Next, the second proposition states if two heat engines have the same efficiency, if they are both if the two heat engines are both reversible, then they must have the same efficiency. If they don't, then we can use the same way to prove it. That means we combine the reversible one with another reversible one. This is going to be reversible one, but this one will have higher efficiency. We want to prove it's impossible. Then same thing will happen. That means we restore the heat from low temperature reservoir, reject at a high temperature with certain amount of work. And if we have a second heat engine, which is also reversible, but it has high efficiency, so we only need to restore part of the work to drive the refrigeration cycle, and then use the rest of the work as something else. And then if we take this as a control volume, net work is produced. So this slide shows Carnot cycle has the highest possible thermal efficiency. On this slide, we discuss the Carnot cycle's efficiency how it's related to the temperature of the reservoir. When we discuss the Carnot cycle, we did not discuss the state of the fluid at each stream, except we discussed the temperature. Remember, we discussed Carnot cycle, we only discussed T high and T low. We didn't discuss the pressure at all. We did not discuss what kind of fluid it is. Therefore, it makes the scientists wonder if the thermal efficiency is related to temperature. As we discussed earlier, a heat engine, its efficiency can be expressed as 1 minus QL divided by QH. So that means if a Carnot cycle efficiency depends on temperature only, that means QL to QH depend on the two temperature only. This is a very interesting hypothesis. Indeed, we can prove that this ratio indeed equal to QL divided by TH if the working fluid is ideal gas. It's proved in the textbook in section 5.8. We're not going to discuss the detail, but this is a very important conclusion. If ideal gas is used as a working fluid, the thermal efficiency can be expressed as 1 minus TL divided by TH. Very simple algebra expression that has important implications. Number one, when this is derived, we have to know the absolute temperature scale is used. So that means the Kelvin, the temperature in Kelvin should be used in this expression. Number two, it proves what we mentioned before. The thermal efficiency not only depends on the temperature difference, this means the temperature ratio has to be as low as possible to drive the thermal efficiency up. This is a very important conclusion. Let me say it again. The thermal efficiency of a Carnot cycle depends on the ratio of the two temperature reservoirs, and the temperature ratio should be as low as possible to keep the thermal efficiency as high as possible. Now we look at the heat engine's efficiency. We can all do this calculation very easily. This is idealized efficiency. If we fix TL, like a boiler, the heat is rejected at the ambient condition, near the ambient condition. And this axis represents the boiler temperature. So the boiler temperature has to be as high as possible to make the efficiency as high as possible. This curve represents this formula. In reality, however, we look at the four types of heat engine: coal-fired power plant, nuclear power plant, gas turbine burning natural gas, car gasoline engine, have these typical running conditions. So these are the calculated idealized efficiency. It ranges from 0.55 to 0.6. But in reality, we can only reach a number between 30% to 50%. A lot of the heat is lost. And then if we look at the COP, the coefficient of performance of air conditioner or freezer or refrigerator, it represents this way. The COP is defined this way earlier, and we can convert to a simpler form like this. From this step to this step, we simply divide each term, each factor by QH. By QH, we get a 1, divide QH by QH. Then this ratio QL to QH can be represented by TL to TH. Then we multiply each term by TH. We get this expression. Then we can plot in this way. In this blue curve, we fix TH. The horizontal axis represent TL for the blue curve. And again, the higher the temperature of TL, the higher COP we'll have. And on the right-hand side, we fix TL and plot TH, the horizontal axis represent TH. The COP for heat pump can be represented in this way. And comparing to the reality, this is the idealized COP. It ranged from 3.3 to 7. In reality, we can get COP only 2 to 4. Okay, this concludes my discussion of reversibility, Carnot cycle, and how these two characteristics of heat engine can be applied to the analysis of heat engine and heat pumps. In the next segment, I'm going to discuss a few examples. This concludes this segment.